Hello class. Today we will be talking about what is this? Parallel circuit inside of our unit, electricity and magnetism. So here we have is a parallel circuit of a kitchen, which has one, two, three, four, five, six different appliances connected to it. Our job was to find the amps, I believe, the amps of each, and figure out whether if everything was connected and plugged in at the same time, whether it would set off the breaker or not. So what we did to do that is we already had the we already had the volts, which is 120 volts per every single for every single. It's just standard for every household. So we had to look at each appliance and figure out how many watts it was, and from that we can do watts over volts and get the amount of amps, the current going through each one. Because it was a parallel circuit, the voltage remained constant throughout each different appliance. So then calculating all that, you get, a separate number of current for each different appliance. And then you use that and you add it all together. And then what you'll get from adding every single current together is you'll get the amount of current that'll be running through the system at this point in time, and then again at this point in time. The breaker is set up in right here, meaning that it'll get the brunt force of everything coming together. Because as the current leaves, a part of it goes through here, which is 1 amp, as seen here. Part of it goes through here, which is 1 amp goes through here. 10.8 amps goes through here, this one. So like that, and then back here, it gets the full brunt of it, which in this case is 23.09 amps. So then according to this, our poster here, that would set off the breaker. I can't tell where or how much the breaker is, but that would set it off, apparently. Here, the current maximum is 20 amps. 23 amps is 3 amps over, so if all of this ran at once, it would set off the breaker. And after that, we could figure out how much money we were spending on this circuit if it was running non-stop for 24 hours in a month-long period. So to do that, you just did the equation here: kilowatts hours times the amount of money per kilowatt hour. So to find kilowatt hours, you just multiply the kilowatts times 60 minutes, and you get that times 0.07, which will give you 139.74, which is $139 approximately. So yeah, that's our thing. Hope you enjoyed it, I guess. So yeah. Hello. Today we will be talking about momentum. Momentum is a big topic in physics, and this is what I decided to do my spring break project on. Alright. So what is momentum? Momentum is defined as the product of mass and velocity of an object. Momentum is vector, which means it possesses direction as well as magnitude. So you could say momentum is moving this way, and it also is moving this amount, or the other way in a different amount. Well, this is unprofessional. That's okay. Momentum is calculated using mass times velocity and is represented by p. This equation basically tells you that mv equals p, and then you can substitute p in wherever you see mv, or the other way around. The law of conservation of energy. This states that the total amount of energy in an isolated system remains constant over time. For an isolated system, energy can change location or, form within the system, but it cannot be created or destroyed. We'll get more into this in a little bit. Application to momentum. In a closed system, momentum cannot be added or lost. Due to this, we can create an equation with two or more objects with momentum, because total momentum of the system of the two or more objects will be the same as before, as it is after any interaction between them. The equation for this is like this, basically. So we have object 1 mass times velocity, which is p, momentum of that object, plus object 2, its mass times velocity, momentum initial, which means before any interaction between 1 and 2 took place, is equal to mass and velocity of object 1 plus mass and velocity of object 2 final after the interaction took place. We can do this because of the law of conservation of energy, which means that the energy in the system remains constant over time. So then this would initial momentum would have to equal. Have I been going for 5 minutes? Wow, that's insane. Anyways, initial velocity equals final velocity. Okay, so the total momentum is constant, even though it changes maybe from one object to another object, and any number of objects can be added. That's really important because here in this situation I only have 2 objects, but then you can have an infinite number of objects, 1, 2, 3, 7, 12, 15, as many as you want, as long as the initial velocity of all those objects after and before an interaction equals the amount after an interaction. Finally, the only problem with this law here is that it doesn't really apply to any or many situations in our universe, because, well, here, let me just read it. Unfortunately, no situation in the world allows the law of conservation of energy to actually behave, because nothing is a true closed system. What this means is you can have 2 objects, but then there will always be an outside force acting on them. Like if you have 2 cars, no matter what you do on Earth, you're gonna have friction on the ground, which will lose some of that energy. Or 2 objects that are falling, you'll have air resistance or other things that'll keep the systems open. So as much as like we can use this to basically approximate with this equation, we're never gonna get it perfectly because of uh, open because of things that open the system like friction, air resistance, etc. Thank you for watching.